We're talking about geometric imaging. The last couple of episodes talked about pinhole cameras and coated aperture imaging, which is kind of obscure really from a practical point of view. But today we're going to talk about very practical systems, projection tomography. The image on the left is using a visible camera to do optical projection tomography of soap bubbles. So the big yellow cylinder is a piece of plexiglass, and inside is some soap that's been mixed up to make bubbles. The images on the right are vertices within those bubbles. Prior to this image, nobody had ever really looked at how vertices form in these bubbles, which is of interest to geometers. But we can use projection tomography to form very accurate 3D models of such systems. Worldwide, there's 1 million medical CT scans every day for biomedical imaging. The US has about 1.5 million a week. But more than 10 times that many are done at airports every day. Here we see an array of CT scanners at an airport to scan bags. So this is a very important common technology. Let's figure out how it works. Computational imaging. Episode 22, Projection Tomography. Tomography is the most core problem in computational imaging. It deals with how to reconstruct high-dimensional objects from measurements embedded in a lower dimensional space. There are many different forms of tomography. There's an example of diffusion tomography, which uses the diffusion equation to describe signal propagation inside of objects, but then measures the signal on the outside of the object. This is an example of reconstruction of blood density inside of a tissue phantom. There's diffraction tomography, where the field inside of the object propagates according to the wave equation. These are examples of different slices of an object reconstructed in a volume from diffraction tomography. We'll talk about diffraction tomography in Chapter 5. There's magnetic resonance imaging, which measures radio wave signals from magnetic resonance. This is a picture of actually my own head taken in a magnetic resonance imaging system. This doesn't really use wave propagation, so we don't talk about it in this course. There's spectral tomography, which involves reconstruction of the three-dimensional space-time data cube. We will talk about compressive strategies for for spectral tomography in the course, but today we're talking about projection tomography, which is basically reconstruction of objects from the shadows of geometric rays propagating through the object. The geometry of projection tomography is shown on this slide. We have an object which occupies the region at the center of this circle here. Here's our object. And we're going to measure rays through the object. So we're going to measure projections that propagate through the object. So let's say along the line here, propagating at some angle theta relative to the x-axis, a distance L away from the origin. We would calculate our measurement as the integral of the density of the object along that line. This model is based on Beer's law, which suggests that there's exponential attenuation in the ray due to the density of the object. We can linearize the object into this integral form by assuming that the modulation is relatively weak, as discussed in the text. Now, assuming that this is our measurement, now we have our forward model for projection tomography. We can vary the distance of the ray from the origin, L, and the angle of the normal of the ray that propagates through the objects. We have a two-dimensional set of measurements, G of L and theta, which is operating on, in this case, a two-dimensional object F. So we're measuring the object in the plane from measurements outside of the region of the object taken at various angles and distances from the origin. Now the interesting thing is we need to find, of course, an algorithm for estimating F given G, but if we take the Fourier transform of G with respect to L, we get an interesting result. So we've, in this first integral, taken that Fourier transform with u sub L being the Fourier transform variable in G. Now we can substitute into that our integral form for the measurement from here. We're substituting this integral in to get that equation in terms of F. And then we can substitute for F its Fourier transform, where we've also operating on it with the inverse Fourier transform over U and L. But we can integrate now over all of the variables except U and L which would be this integrating these exponential terms, which of course integrate to a delta function. So then that delta function is integrated over U and L to give us this result, that the Fourier transform of the measurements with respect to the distance of the measurements from the origin is equal to the two-dimensional Fourier transform of the object density evaluated at along a line in the two-dimensional space of that Fourier transform. That line is the slice. So the Fourier transform of our set of measurements with respect to L for a given angle is equal to the slice of the Fourier transform of F. So that's kind of interesting. Now we have basically related our measurements to the Fourier transform of F. In principle, we could just now inverse Fourier transform from F to get our reconstruction. Before we do that, let's look at what the measurements might look like. So in this section, we're using these minced digits as our model objects for playing around with this algorithm. What we see on the left of each pair of images is the digit blown up to a scale that is useful for us. And on the right is what's called the sinogram. This is what the measurement data would look like. Now, the horizontal axis is theta, so these are different angles theta that we're propagating the line integrals relative to, and the distance, vertical distance, is L. So when L gets large enough that the circle, the distance of the ray is outside of the region that the object occupies, we get these black regions. But when we're integrating along a ray that goes smoothly through the object, let's see if we can go smoothly through this object, then we would get a bright spot in our sinogram. So this is what the measurement data looks like. This is taking two-dimensional objects and making two-dimensional measurements, but measurements outside of the object. So along each for each angle of the illumination, we take a one-dimensional set of measurements for L, and then we make that into two-dimensional by varying the angle to different directions. Okay, so now how are we going to invert this Fourier transform to estimate the original object? Now the problem we have is when we measure these slices through the Fourier transform, we get a very non-uniform sampling in the Fourier space of F. And so people have developed this convolution backprojection algorithm which appropriately weights the measurements to get a better conditioned reconstruction. So we have our measurements G sub L. We Fourier transform them to get the slice in the Fourier space of F. But now we multiply by a filter, because the thing about this slice is we have many more samples close to the origin than we have at the edges of the Fourier space of F. And so I'll motivate why we multiply by this filter function, but this is the convolution part. We have a filter function. And then the back projection part is we're going to sum the filtered functions to get our reconstruction. So this is the convolution back projection algorithm, which was developed in the late 60s, early 70s for projection tomography. To understand the algorithm, let's just look at our function f of x, the density of the object that we want to evaluate. We can write the Fourier transform of f in angular coordinates instead of in xy coordinates, and if we do that, we get this form. So this is just transforming f is equal to, of course, to its own the inverse Fourier transform of itself. But if we express that inverse Fourier transform in angular coordinates instead of xy coordinates, we get this form, and there's this weighting function magnitude of w, which naturally comes into the cylindrical coordinates that we're evaluating this Fourier transform in. We can write this f now is equal to the integral with respect to theta, so summing and back projections of this function q. Now it turns out this function q is exactly, G of L, our measurements, which are what we're going to use to represent, the Fourier transform of f along a particular slice, weighted by this frequency coefficient U sub L. So this algorithm looks like this. We would have here a particular object. This is the sinogram of the object. Now, if we take the sinogram and we take its Fourier transform, it has a lot of DC components, so the Fourier transform is heavily weighted toward the origin. So this is a Fourier transform along this L axis, the vertical axis, as a function of theta. Here for comparison is what the Fourier transform of f looks like. So we've kind of taken it, which is the object has non-negative density, so in this case, the Fourier transform is highly centered at the origin. We've kind of unwrapped it with respect to theta to get this this version of the slices, but we weight that by the magnitude of the Fourier coefficient, and what that does is emphasize the high frequency. So this is taking this function and weighting it by the filter function, and then we back project that to get the reconstructed object as shown here. Here's an example of the convolution back projection algorithm for a different object. You see the sinogram has patterns in it from the periodicity of the object, and we get its Fourier transform with respect to L, the weighted filtered function, and the back projection reconstruction. Here's an example of that for one of these minced digits in the code that's given in the course. In the GitHub site, these digits are used as examples, and so we have again the Fourier transform of the digit, the measurement, the Q function, and then the back projection reconstruction of the image. So that's all well and good. That was a great algorithm, developed specifically for CT. This is a two-dimensional system. As I told you, we're talking about high-dimensional objects reconstructed from lower-dimensional spaces, and in this case, on a ring around the object, we're going to measure projections for different illumination directions. We've matched actually the dimension of the measurements to the measurements of the object, which is commonly done in tomographic systems to make the problem easy. We're not always going to take that approach, and so we'll talk about compressive sampling strategies where the dimension of the measurements is lower than the dimension of the object, but we're not quite there yet. Let's try to understand exactly how conventional algorithms work. So this algorithm, is kind of a workhorse, and there's generalizations of the algorithm that work when you go to three-dimensional objects, where you're going to sample the object with a cone beam sampling strategy instead of this what's called a fan beam or plane wave projections that we've done in this first part of our reconstruction. There are, of course, many different algorithms. All the algorithms we talked about in Chapter 3 could be applied. In just a second, we're going to use a neural algorithm to do some reconstruction. If we don't want to do convolution back projection, one of the problems is that the algorithm doesn't necessarily respond well to incomplete data, which is what we're going to want to do if we would want to form a compressive measurement system. Another approach would be to use algebraic estimation. Of course, this is a linear system. We've written a linear, integral equation to describe the forward model. We could discretize F and discretize the measurements and turn this into an algebraic form. And now we could use any of the algorithms we talked about in Chapter 3 to do the reconstruction, but we'll often run into the problem that the dimensionality of the data is high, that maybe we're going to reconstruct megapixel images or better, and so this there may not be simple symmetry in H that would allow us to find an efficient algorithm, and so a variety of different algebraic algorithms have been developed to estimate the reconstruction. These iterative algorithms operate on a row by row. This is what's called simultaneous algebraic reconstruction. It's a popular reconstruction algorithm. It takes each component of H, each vector in H, and then tries to make the estimate of the object consistent with that single vector in the H matrix. And so this is the regression error on that single component, and we try to iteratively go through all of the rows of H to try to minimize the regression error. Rather than trying to invert the matrix in a single step, this does this row by row, and this can be shown to converge under appropriate circumstances. We're going to use this algorithm to reconstruct systems with incomplete measurement. So we have shown that if we have the complete set of rays going through an object, we can reconstruct the object using the projection and slice theorem. Here we have a vertex of points. This is common with X-rays, that the X-ray is going to come from a single point. Rather than measuring a parallel set of rays going through the object, we measure a fan of rays that come from a certain vertex point, and then we can move the vertex point around the object to try to sample all the rays through the system. Now, there are various ways that we might choose to subsample the rays. The reason we would want to subsample the rays maybe just to show that we don't need all the data that we need, but there's a cost to illuminating a object with an X-ray. So if we can reduce the number of X-rays that we need to reconstruct the object, we might reduce the power that we've illuminated the object with, and show that we can minimize the damage we do to the object while we collect the data. So the question that we might face is, if we subsample the data, what would be the appropriate way to subsample the data? In this particular case from this paper, this is what the singular value decomposition of the object space looks like for different features in the forward model if we take the vertex points and uniformly subsample some of the vertex points. So we don't use a complete set of vertex points. This, on the other hand, is what happens what the singular vectors look like if we randomly suppress some of the rays in each one of the fans. And what you see is a more random looking singular value decomposition, which may be more effective in capturing the details of the object, because the features in the singular value decomposition are higher frequency. So we can compare these different strategies, certainly using a given algorithm, for example, the algebraic reconstruction algorithm. In this particular case, for the set of objects shown on this slide, we have these reconstructions in the center. So this is reconstruction with sparse sampling, with random subsampling on the center row. And then at the bottom, we've taken the algebraic reconstruction and used that as the input to a neural network to estimate the underlying object, which hopefully can recognize the artifacts coming from the subsampling and correct them. The code that generated this is on the course GitHub site. So if you go to the GitHub site and look at this code, you can see exactly how this was done. The neural estimator was a very simple sort of convolutional U-net that goes from a large image with a small number of features to a small cross-section with a large number of features, and then back out to the estimated image, trained on the minced data set of numbers to do this simple demonstration. What we want to show here is what happens when we subsample versus when we fully sample all the data. And here are the results of that analysis. At the upper left, we have randomly compressively sampled data, I think sampling 10% of the underlying rays in the system. At the top is the algebraic reconstruction from the compressively sampled data, and at the next row is the neural estimated image from the compressively sampled data. At the lower right, we have the same thing with fully sampled data. So we've measured the full set of rays through the object, and the top is the algebraic reconstruction, and the bottom is the neural reconstruction from that data. And what you'll notice, hopefully, is that the compressively sampled data, or compressively sampled estimated images, are better than the fully sampled ones. The reason that both of them have some defects is that we added noise. So we assumed that the number of photons used was limited, and both of them used the same total number of photons with Poisson noise added to the measurements. And so the idea here is that as we reduce the number of photons in any kind of measurement system, the image will degrade, but we're better off to measure a compressively sampled set of data that may have higher information content because of lack of redundancy by not sampling totally adjacent rays, and that then we show that compressive sampling can yield a better result than fully sampled data. This is the kind of trade-off that we're very interested in computational imaging, and we'll talk about throughout the course, about choices, about why we make certain measurements, and what the rewards and costs may be. So that's how projection tomography works. Projection tomography can work at X-ray systems. It can also be used in optical systems. A lot of times we can model a camera by a certain ray model to say that each pixel on a camera measures the ray through the object, just, ignoring defocus and wave propagation, but just saying everything is in focus within the depth of focus of the object. Each pixel measures the ray through the object space. That can be true for actual volume objects, like here we showed with this foam image that we started the the lecture width, that we have a translucent object, and we can assume that the density we see along each ray is proportional to the density of the object along that ray. We can apply exactly these projection tomography algorithms to do three-dimensional construction with optical projection tomography. Okay, so that's an example of a very practical system used millions and millions of times every day around the world. Next day, we want to go and talk about how to make that better. So we've talked about we could modulate the rays of the X-ray source. This is now a coding problem about what kind of strategy do we want to get into to code the forward model. We can code, in this case, by structuring the illumination by choosing which rays illuminate the object. We can also code by structuring which rays propagate to the detector array through some geometric model. And we can expand on our strategy for better compression and better performance through coding. Let's talk about that in our next episode.